Hello students. So in the previous lectures I was discussing about 8085 microprocessor instruction set, and in that I was discussing about the arithmetic group instructions. So the next instruction I will be continuing with the same group only. So the next instruction is DCRR. So DCR represents decrement. In the previous lecture I was discussing about increment. Now in this lecture I will be discussing about the decrement instructions. So the next instruction is DCRR. So here R represents this R represents the register. For example, DCR B. It can be any register. R can be any register. It can be B, C, D, E, H, L, any register. So what this instruction will do, it will decrement the content of the register, whichever register is mentioned. For example, here I have taken register B. So what it will do, it will decrement the content of register B and store the result in the same register. So here I have written also decrements the content of the specified register by 1 and stores the result in the same register. So for example, let us take an example. Let the content of B is 21H. So after execution of this instruction DCRB, what will be the content of B? It will be 20H. So the content of B is getting decremented by 1 and the same will get stored in the same register. Now number of flags, how many flags will get affected? So again, this is DCRR. In this, all flags, since it is a arithmetic group instruction, so all flags will get affected except carry flag. Why carry flag is not getting affected in this type of instruction? Because if suppose if the result, if suppose the DCR B, if the content of register B is 00H, if the content of register B is 00H, then if we apply this instruction DCRB, what will happen? The content of register will get decremented and the result will get stored in register B. So here what will happen? Decrementing means it will get, the content of register B will get equal to 1. Let me do it in this way. Suppose the 8-bit content is 00000. It will be more easier for you to understand this thing. So suppose the content of register B I have written in binary format here. Let it be 00000000. So after decrementing, what it would be? After the after execution of this instruction, the content of register B will be 11111111. So that's why whenever we increment any register or we decrement any register, the carry flag doesn't get affected. All other flags will get affected, but the carry flag will not get affected because it is not going to raise, the increment or decrement operation is not going to raise any carry, because if the highest number is stored in any register and if we apply increment, suppose 11111111 is stored in any register, and if we apply the increment instruction, then what will happen? It will move back to 000000. That is this. And if we if any register is having this content and if we apply decrement instruction, then what will happen? It will move back to this. So no carry flag will not get affected in this type of instruction. Now next, how many bytes of this instruction? So since there is no hexadecimal number mentioned along with this instruction, so this instruction will have only 1 byte, and that too for the opcode. So how many machine cycles will be needed? Here I have written only one byte instruction. How many machine cycles are used for this type of instruction? So only one machine cycle, and that too for opcode fetch. So after fetching the opcode, microprocessor will get to know it has to decrement the content of a register and store the result in the same register. And since the register is present inside the microprocessor, so it will not need any extra machine cycle to execute the whole instruction. So only one machine cycle is enough for the complete execution of this instruction, that is opcode fetch machine cycle. Now T states since opcode fetch machine cycle has 4 t states, therefore this instruction will need only 4 t states for the complete execution of this instruction, for its complete execution. So you have written 4 t states. Addressing mode, since the operand is the content of the register, so therefore the addressing mode here is the register addressing mode. So you have written register addressing mode. Now next instruction is DCRM. So what DCRM does, it is again a decrement instruction. It will decrement the content of memory location which is pointed out by HL pair. For example, the content of HL pair is, let it be 6050H. Let the content of HL pair is 6050H. Then the memory location whose address is pointed out by HL pair, that memory location is having the address 6050H. Now let us suppose the memory location having the address 6050H, it is having the content 32H. Now after execution of this instruction, so after we execute DCRM, what will happen? 32H will get decremented by 1 and the same will get stored in the same memory location. So what will happen after the execution of this instruction? 32 will get decremented by 1 and the result is 31H, and this 31H will get stored in the same memory location. Flags affected, again all flags will get affected except carry flag, because if the number, suppose if the content is 00H, then, or you can say if the content is, if I write it in binary form, if the content is 0000000, if the content of memory location is this, and if I decrement it, then no borrow flags will get generated, or no carry flag will get set or reset. What will happen on decrementing it? It will get switched to this number 11111111. Now next instruction, so here I have told you about this DCRM. Now flags affected, all flags will get affected except carry flag. Now number of bytes for this instruction, since no hexadecimal number is mentioned along with this instruction, so the number of bytes will be 1 only, that is for opcode. Now how many machine cycles are needed for the complete execution of this instruction? Now DCRM for the complete execution of this instruction, what will happen? First machine cycle will be used for opcode fetch. After fetching the opcode and decoding it, microprocessor will get to know that it has to decrement the content of memory location whose address is pointed out by HL pair. So microprocessor is having the address, but it has to read the content of that address. So second machine cycle will be used for reading the content of the memory location whose address is pointed out by HL pair. Now once the microprocessor gets the data, it will decrement it, and the next machine cycle will be used for writing that data into the same memory location whose address is pointed out by HL pair. So 3 machine cycles, 1 opcode fetch, 1 memory read and 1 memory write. So all total 3 machine cycles. So opcode fetch will need 4 t states, memory read will need 3 t states, and memory write will need 3 t states. So all total 10 t states. So here I have written also 10 t states. Here I have written 10 t states and 3 machine cycles. And addressing mode, since the address of the operand is indirectly specified by HL register pair, so the addressing mode is registered indirect. Now the next instruction is DCX-RP. So DCX-RP, again it is a decrement instruction. It will decrement the content of register pair. RP can be any register pair of 8085 microprocessor like DC, DE, HL, and when you are mentioning the register pair in the instruction, you have to mention write that register which is carrying the most significant byte, most significant byte of that register pair, of that 16-bit data. So like in BC you will write B, in case of HL you will write H, in case of D you will write D. So DCX, what it will do, it will decrement the content of register pair, and it will store the same decremented content in the same registered pair. Flags affected, no flags will get affected. I told you when I was discussing that INXRP, when I was discussing the instruction INXRP, and here also you can see that since it is since it falls in arithmetic group, you might think that it is falling under arithmetic group and the flags should get affected, but in these two instructions the flags are not getting affected. Why? Because very technical reason is that because in 8085 microprocessor, whenever any registered pair is storing any 16-bit data, so that registered pair always stores the address. What I am trying to say is that suppose BC register pair, suppose it is storing the data, it is having the data 6050H. So this 6050 is actually the address of a memory location. So whenever registered pair is storing, whenever any registered pair is storing any 16-bit data, that 16-bit data is representing the address of a memory location. So whenever I am using any increment or decrement operation on this registered pair, I am actually incrementing or decrementing the address. I am not incrementing or decrementing the content of that memory location or anything. I am incrementing or decrementing the address. So that's why it has been made in such a way, the 8085 setup has made up in such a way that whenever I will execute these type of instructions, INX and DCX RP, it will not affect any flags, because incrementing or decrementing the address should not affect any flag. When you are performing any arithmetic operation over any content of register or over any data or over any content of memory location, then the flags should get affected. Otherwise, what will happen if you are incrementing or decrementing the address and the flags are getting affected, it will provide serious issues in the later stage of the programming. So that's why flags affected for these type of instructions will be nil, no flags will get affected. Now number of bytes of the instruction is 1 byte, because there is no hexadecimal number mentioned along with this instruction. Machine cycle, how many machine cycles we need? So as I've told you, in INX RP case also, it will need only one machine cycle, that is for fetching the opcode, because the register pair is present inside the microprocessor. So one machine cycle will be used for fetching the opcode and decoding it, and once the instruction gets decoded, microprocessor will get to know that it has to decrement the content of register pair, and that register pair is present inside the microprocessor. So the microprocessor will not have to perform any extra machine cycles for the complete execution of this instruction. So only one machine cycle is enough for the complete execution of this type of instruction. And T states, since after decoding it, this type of instructions will need larger amount of time for the execution purpose. So this type of machine cycle, so this type of instruction will have 6 T states, will have 6 T states for the opcode fetch machine cycle. So why not 4? Because it will need more time for executing the instruction. Because what is happening, it is actually fetching the opcode, decoding it, and then what is happening, it will decrement the content of register pair, and it will store that content of register pair. So these things will take time. So that's why 6 T states. Addressing mode, since the content is the since here the operand is the content of register, here the operand is the content of register, so the addressing mode will be register addressing mode. Now the next instruction is DADRP. DADRP, what it will do, it will add the content of register pair with HL pair. So whatever register pair is mentioned, suppose DADB, So what it will do, whatever is the content of HL register pair and whatever is the content of BC register pair, it will add that content and it will store the result in the HL registered pair. So in DAD RP, flags affected, only carry flag will get affected. Number of bytes, since no hexadecimal number is mentioned along with this instruction, so number of bytes will be 1. Machine cycle, it will need 3 machine cycles. How 3 machine cycles? That I'll tell you in my next lecture. So okay, I'll be discussing this DAD RP and decimal adjust accumulator, these 2 instructions briefly in my next video lecture. I'm ending this class here. Thank you.